Hello, Stats 300, and this is Professor Gonzalez, and I would like to do some problems for you in the section of, let's see, this is the interactive ALEKS section, signified with the symbol of this or this. Let us know that we're on the interactive ALEKS side, 7.2. Okay, so let's take a look at this first one. It says, suppose that the antenna lengths of woodlice are approximately normally distributed with a mean of 0.22 inches and a standard deviation of 0.05 inches. What proportion of woodlice have an antenna length that are more than 0.18 inches? Round your answers to at least 4 decimal places. So I think what I want to do here is collect some information. The mean antenna lengths for these woodlice are 0.22 inches with a standard deviation of 0.05 inches. Okay. Now, let's look at the raw data just to kind of get a picture of what's happening here. Let's see if I can squeeze all this in. The screen is a little bit small. With the raw data, the mean antennae length is 0.22, and we're looking, the question is, what proportion of woodlice have antenna lengths that are more than 0.18? Well, 0.18 is definitely to the left of 0.22, so it's smaller than the mean. So this is 0.18. Notice this is not a negative number because they're not z-scores. It's not a standard normal. This is our raw data from the problem. We want to know what proportion of woodlice have antenna lengths that are more than 0.18. So that's going to be, we need to find the area under the curve to the right. Now, of course, we cannot use our z-table if we don't have z-scores. So we need to turn this information into z-scores, and we can do that by using our formula, and that is going to be z equals our x value, which is 0.8, minus the mu, which is 0.22, all divided by standard deviation. Oops, that's a funny 5. Okay, now when we continue on with that, in the numerator, we get negative 0.04 over 0.05. With the calculator, we find out that that is, I might not even need a calculator, negative 0.8. Okay, so that's our z-score that is associated with the raw score of 0.18. Okay, so our new picture looks something like this. Of course, now this is a standard normal, so we all know that. Excuse me, the mean is going to be 0. And our z-score that represents the 0.18 in the raw score, that z-score, when we used the formula to convert, is going to be about here. And that's just a negative 0.8. And we're looking for, remember, the length of antennas that are more than this. So it's going to be to the right. And, we end up running into the same little dilemma each time, because when we look up negative 0.8 on our table, that is going to give us the area, once again, area to the left, because that's what z-tables do, which is this stuff right here. And when we look that up on the table, I think you guys are good at looking. Let's look at the table one more time, and we'll look at the table on the last problem, because last problem we have to go in backwards fashion. But when we have a z-score, let's look it up. Negative 0.8, that's going to be down here. A z-score of negative 0.8. And there's negative 0.8. And of course, when there isn't any more value past that 10th spot, then you just use this column. Negative 0.8 has an area. Whoops, somehow it changed over to eraser. Okay, there it is. So it's 0.2119, 0.2119, 0.2119. Let's get back there. Of course, that's the area of that. We don't want that. We don't want the green. We want the gray. How do we do this? No problem. We just take that green and subtract it out, right, from a value of 1, because of course the area under the curve all equals 1, the total curve, right? So if you subtract 1 minus 0.2119, we get this remaining gray shaded stuff over here, which ends up being 0.7881. So the area, so what are we looking for? The proportion of woodlice that have antenna greater, so let me see where we're at. What proportion of woodlice have antenna lengths that are more than 0.18? Well, that's going to be these guys over here, which is 0.7881. They said proportion, so we just leave it as a decimal instead of, don't write it as a percent because they didn't say percent, even though that wouldn't be a massive foul, I don't think. But anyways, here's the answer. If you thought about it as percent, right, that would be what? Oh, that just jumped. About 78.8% of these wood lice have antennae that are more than 0.18. All right, next problem. Next problem, we're talking about a biology researcher. Okay, and this biology researcher is studying the risk of extinction of a rare tree species in a remote part of the Amazon. In the course of her study, the researcher models the trees aging using a normal distribution. Once again, just like last problem, it said normal distribution, which allows us to use, the normal distribution curve, which is important, right? If we don't have that, then we can't use our z-scores. With a mean of, so let's take some notes again. We've got a mean of 251 years, and this is the aging of these special trees that she's researching, and has a standard deviation of 50 years. 50 years, okay? All right, I like looking at the raw data just to kind of get the big picture here. I am running out of space on this one a little bit because I copied in the middle, but anyhow, let's see if we can draw this real small over here. If I can fit it in. Oof, that's really... Anyhow, there it is. And this is the raw data. Oh, and this is going to be really tough to squeeze this in because let me continue to read the problem. Let me have a different take on this. Let's see. Let's go ahead. Let's go ahead and put the raw data up top here, and then I'll do my z-score down below, down here, okay? So let's see if we can get that together to happen. So I'll make this a little bigger so we can make sure we can really see it. So the actual mean of this is tree ages, right? The mean is 251. This special tree and has a standard deviation of 50. We get to the question here. Use an ALEKS calculator to find the percentage. Use an ALEKS calculator to find the percentage of trees. We can also do this with a table. We're trying to find the ages of trees between 187 and 229. Well, 250 is the mean. So 187 and 229, that's below the mean. So it's going to be something like this and something like this. So we got 187 years, and then this one was 229. And how do we know it's in between is what we're looking for. Ooh, getting a little sloppy there. Because it says find the percentage of trees with ages between 187 years and 229 years according to the model. Okay, give your final answer in 2 decimal places using percents, because they're asking they asked us find the percentage. So we need to write that as a percent. Now this, once again, is just raw data, right? Not z-scores. So we've got to figure out the z-scores for this. First one, z equals 187 minus the mean, which was 251, over the standard deviation of 50. What does this give us? A negative, 187, negative 64 over 50, which gives us a z-score of negative 1.28. So that negative 1.28, let me use some color just to really drive home what's connected here. The raw score of 187 years is going to convert on our standard normal as a negative 1.28. Okay, let's do this one in red. All right. So now we need to find a z-score for tree age, excuse me, of 229. So 229 minus a mean of 251 divided by the standard deviation. And this, let's see, 229 minus 251 gives me a negative 22 over 50, which means this z-score is negative 0.44. And I'm going to use a little color showing that this tree age corresponds with this z-score. Seems like it zoomed in a little bit on me here. Okay, so now I'm going to use this space down here to write my standard normal curve and do the rest of my work. Oh, that's not the color I wanted. Probably didn't really matter that much. Okay, so we need to make a standard normal curve. Standard normal curves have a median or mean value of 0. And let's go ahead and finish this off now. This has a z-score of negative 1.28. That's this green one. And this z-score is negative 0.44, and that's the red one. Let's put a little green with the green and a little red with the red. And remember what our job is we're trying to find, where was the language? Percentage of trees with an age between 187 and 229 years. Now we have the corresponding z-scores that go with those ages and everything in between, and that's, we could find the area between those two z-scores. I could figure out the answer, which would be the percentage that have those ages between 187 and 229. Okay, well, just like before, I mean, this a lot of repetition here. It's just, now this is a word problem, so that's what makes this one maybe a little bit tougher. But from now on, it should be really familiar. All right, if I got to look this up on my z table, and when I look up a z-score of negative 1.28, I'm going to get an area of 0.1003. And when I look up, I need to figure out this area that goes from here all the way down to the left-hand tail, all the way through the green. When I look up a z-score of negative 0.44 on my table, I get 0.3300. And how do I get the shaded stuff? No problem. We've done this before. 0.3300. Don't really need to have all that in there, but subtract out the smaller area, which is the green one. The red area goes, remember, all the way from negative 0.44 all the way to the left. So we subtract out the green. And why did my pen not work? There we go. The green, which is 0.1003. And we'd like to subtract that out. And when we subtract that out, we get 0.2297. That would be the area of the shaded. They asked us to please find the percentage, and they're also giving us an example. Write this as a percentage to 2 decimal places. Well, all we have to do is take our decimal value and move it 2 places to the right. And now this is a percentage. So the answer is 22.97%. And let's find the percentage of trees with ages between 187 years and 229 years. Well, that's 22.97% trees have ages between 187 years and 229 years. Yay, done. Okay, let's take a look at the last problem here. And I think I'll probably fit most of the information above it. This one's kind of coming at us in a little bit of a different direction. You can't really tell until you start looking at it. And that's why I think drawing the picture does help a lot with this kind of thing. According to her doctor, Mrs. Brown's cholesterol level is higher than only 5% of the females age 50 and over. The cholesterol, so her cholesterol level is higher than only 5%. Well, if it's higher than only 5%, she's doing really well, right? If her cholesterol level is higher than like 99% of the ladies out there, then she's in bad shape. I mean, her cholesterol level is way up there, assuming that other people have bad cholesterol levels or there's a whole normal distribution. Anyhow, it does say this is approximately normally distributed. So let's try to get a picture of what's going on here. So this is what I'm going to do. I'm going to do my approximate distribution, approximate normal distribution. And what did they tell us? Let's see. Cholesterol levels among females age 50 and over approximately normally distributed with a mean, of 225 milligrams per DL and a standard deviation of 25 milligrams per DL. And so if I was taking a look at the raw data here, that would be a mean of 225 would be right there. And what is this stuff right here? Okay, let's see. Use another color there. So this says Mrs. Brown's cholesterol level is higher than only 5%. So 5%, is this little bit of the tail. That might even be too much. That's probably too much, but that's my drawing. I'm gonna stick with it. So right there. Now, when they say 5%, we can't write that down here on the z-score, or we can't write that down with our scale down here because this is cholesterol levels, right? They said 5%. 5% is referring to the area. So that's 0.05. Okay, so when they say 5%, they're talking about probability or proportion. They're talking about area under the curve. Now, we would have this problem taken care of if I could actually figure out what this x value is right here, right? If I could figure that out, I got the answer. Okay, so as usual, we're going to need to take a look at this in terms of z-scores because then we can take a look at our table. I think I'm going to try to fit a standard normal curve right there. Oof, getting a little sloppy again. And maybe I try that again. Guess that's kind of bugging me. Watch, I probably won't be able to do any better. Oh man, pressure's on. Okay, so there it is. And now it's a standard normal curve. So this is, our mean is 0. We still have our 5% area, right? That still stays the same. But what we need to do is we need to find here the z value that goes along with that. So how do we do that? Well, we have to go backwards, right? We have to go in a backwards fashion than we're used to. We have to find it the area of 0.05, as close as we can find of 0.05 on the body of our z-tables, and then go backwards and get the z-score there, and then convert it to the raw score over there. Okay, there's our game plan for us. Ready, break, go. Okay, so look for the area in the body of a z-score table of 0.05. Let's see, 0.05. Now let's think about this. If we are positive z-scores, this is more than 50% of the data. So that's 0.05 is like way down here, right? So positive z-score, I don't think so. No way. It's going to have to be here on the negative values. I got to erase this for sure. Stuff's all in my way. Go, get out of here. Okay. So we're looking in the body. So inside in here for 0.05, or get as close as we can. And we see it, 0.0. Okay. So the way you could kind of think about this is, if you thought about it, if you move the decimal point over, just think about like money, it'd be like $5.05. We're looking for, wait, what are we looking for? We're looking for maybe that's a little confusing saying it that way, but we're looking for 0.05, and we've got this extra, this tenths, hundredths, thousands, 10,000s. We've got extra decimals or a value to the right of the decimal. This one is, whoops, that's not where I wanted that. This one is 0.495. So this one is 0.05 or 0.0005 too much, and this one's 0.995 too much, right? Or five, I'm sorry. So this would be tenths, hundredths, thousands, 10,000s. I don't know if you're seeing what I'm seeing, but essentially, and I have a hard time verbalizing this, sorry about that, but 0.05 is just directly between these two, right? Because this one is 0.0505, and this one's 0.0495, right? So what we want is directly, so we want something, so that's a problem with the z-tables, is it can only be so accurate, especially when you're looking at the body of the work inside and going out, because, there's just so many of these values out here. It's really, they can only show so many. If you want to be more accurate, you're going to take the value, let's see, where am I at? Not there. You're going to take the value from this guy, which was negative, yeah, there it is. So a z-score that I would like to take is negative 1.6. Now, if you selected 4 after that, you're not wrong. It's just not as accurate. Or if you selected 5, it's not. It's just not as accurate. That's all. And so when I see something right in the middle, I like to try to be a little more accurate. And instead of saying 0.04, I say 0.04 and then throw on a 5, which puts it in between the 0.04 and the 0.05. Okay. The book will also at times, or the ALEKS will also at times, when you're doing this, going in a backwards fashion, looking at the body of the z-tables, finding areas and going backwards to come up with z-scores. Sometimes the book will just have you use the ALEKS calculator that is right there in the, will be right there on the screen when you're doing the problem, because they know that the calculator is going to give you the exact value. And so that's always a possibility there as well. Let's take this value that we came up with and come up here and then write it in where we have the answer. So this z value that's associated with an area of 0.05 is going to be approximately negative 1.645. Now, the problem is we want to convert this z-score to this raw score, okay? Let's take a look at a new formula sheet that I put down here. You could take a screenshot of that, also post that, but this has the formulas for normal distributions and also for confidence intervals. This is what you're used to seeing. That's to find z-scores. This is the same exact formula, but manipulated and solved for X. So that helps you find raw scores. You can use that same z-score formula to find raw scores, but you would have to, isolate the X, which takes a little more time, which is fine, no big deal. Anyhow, we have that there, so let's use it. Okay, so we've got that formula, which is X equals mu plus Z times standard deviation. So let's use that guy. Here we are. So we can use the formula. Once again, you could use Z equals X minus mu over standard deviation, or you could use this one that's manipulated for this situation to find the raw score. X equals, I gotta remember, mu plus the z-score times the standard deviation. Okay, so what is the mean? The mean is 225 plus the z-score that we found right there in green, might as well match in green, is right there, is negative 1.645. And that gets multiplied by our standard deviation, which is 25. Okay, we multiply and we get a negative 41.125. So 225 plus this, add that together, and we get X equals, or X is approximately equal to 183.875. Round your answers to one decimal place. So we'll go ahead and do that. We'll look at right there. So X is approximately equal to 183.9. And this would be milligrams per DL. On my picture, what we did here was, that this is our z-score that sort of answers the question, but what's the actual raw score that answers the question? That's what we just found right now. That was approximately 183.9, and that would be milligrams per DL. Okay, I hope that helped out. And so she's doing really great, right? She's only 5%. She's, what did it say? She has, Mrs. Brown's cholesterol level is higher than only 5% of the population, right? So there she is, or 5% of the females that are 50 and over. And so there she is at a great spot, and her cholesterol is not bad at all. All right, I hope that helped out, and have a great day, and I hope you stay safe. And